Welcome to this video lecture. This is Mark Scythian. The date today is May 9th, 2019. The title of this video lecture is Calculating Confidence Intervals for Proportions. So this particular confidence interval calculation in statistical modeling will focus on proportions or true proportion using one sample. And again, just like the previous confidence interval video, which focused on true mean, you will need the TI-84 calculator, derive confidence interval formulas, and the random sample data, which we are going to retest, but instead we're going to test for proportions. So the formula to calculate confidence interval proportion sampling is this formula right here, which you may not even need you will not need the TI-84, but you will need to know the z-score, which is the z-star is the z-score, and this is again another critical value which is applicable to proportions, whereas the t-star is proportional mainly to average, true average, or true mean. So if you take advantage of the central limit theorem, you can manually derive a z-score by actualizing the difference between the sample average and the tested average. However, when you move into proportions, you are then using the same methodology in terms of proportions or percentages. So this is all mathematically derived with these coefficients for the given different confidence levels. So again, we're going to focus on a 99% confidence. So in this particular confidence interval for proportion, we're going to, again, use the same survey sample, 109 survey respondents, but this time we're interested in knowing the statistical modeling regarding those survey respondents who selected an 8 to 10 rank on a scale of 1 to 10 in proportion to all populations is sought after for true proportion confidence interval. So by now you should understand what a confidence interval serves its function as, to actualize all populations taking the same survey based on a randomly distributed, unbiased test sample. So again, this is applicable to any system, but for educational purposes, we're focusing on a objective, easy to understand survey which ranks some product on a scale of 1 to 10, and the respondents are from different demographics as to create a random distribution to eliminate any bias. So you can see the ranks are kind of low overall, but they're all over the board basically. Many outliers, and if this was put into a graph or a box plot, it would be a very skewed graph. So this then validates the unbiased survey sampling statistic sample data, or the data set is the proper word for that. So let's just say you want to know what is the confidence interval if all people took the survey for a high rank, let's say 8 to 10. So again, this might be some make, model, and year of automobile, and he took a random survey sampling from all different backgrounds. Again, it's unbiased, it's binomial, a random distribution. It is not a bell curve on the statistic. So the job of the confidence interval is to normalize that into a bell curve, so it's applicable to all population or proportion, all populations to take the same survey. So if 5 billion people were sampled, you'd still get the same result if you had unlimited time and money by just testing 109 samples. But remember, you have to be very careful on how you take the sample data to avoid any bias into the survey. So this isn't something you can cookie cutter. You really got to put the time and effort into looking through all different unrelated population demographics, and then go ahead and survey, in this case, the 1 to 10 rank on a certain product, let's say. So it is a good question to ask. What true proportion of all people who took this survey would pick 8 to 10 for a rank? So you can go back and use this formula here. This is the p hat plus or minus the z-score times the square root of the standard error, which is the probability for success times the probability for failure divided into the number of samples. And then this whole quantity you get the square root of. So you really want to calculate the orders of operation. So do what's in the parentheses first, get the square root of the calculation, multiply it times the z-score, and then rewrite it with the p hat plus or minus this entire quantity. Again, it should be written in parentheses, but to prevent redundancies, it's assumed you understand the orders of operation in mathematics. So we should have a z-score of 2.58. So upon going through the sample here, we count how many people picked an 8, 9, 10. And if you put a few minutes into it and count, you will find that 12 of 109 respondents selected between 8 to 10 rank. So that means the estimate proportion, the p hat, is just 12 divided into 109. So 0.11 or 11% selected 8 to 10 rank. From that point on, you've established the p hat, you have the n, and you don't need the TI-84 because you don't have to do any t-star calculations on this one, but you would simply just enter in 0.11 plus or minus 2.58 times the product of the success times the failure. So the success of getting 8 to 10 is 11% or 0.11 multiplied times the difference of that, the failure. So once you multiply these two out, divide it by the number of samples, get the square root of that, times 2.58, that's the critical value, the z star, you will get 0.11 plus or minus 0.07732. That would be the standard error you calculated, right? Right there. That would be the standard error right there. That would be the z-score or z-star. That would be the initial estimated proportion. So when you do so, right here, 0.11 plus or minus 0.07732, you will get a confidence interval 0.11 minus the standard error, comma, 0.11 plus the standard error. So that translates to between 3.3% to 18.37%. So of course, if you want to verify the calculation and just get the median and mean, because now you've normalized it into a bell curve, it would just be that difference plus the minimum value, you get 11%. So that would just be an estimate. But if you want to know the limits, so what are you dealing with? So you put the same product out on the market, and you took this normalized distribution from a random distribution using central limit theorem, then derived into a confidence interval for proportions. You will get a conclusion, which is we are 99% confident that the true proportion of all populations who took the same survey select a rank between 8 to 10, which equals between 3.3% and 18.73%. You could say 3 to 19%, and it's so important, I kind of kept that out, I'm going to write that in, is of all that's so important. So if you're doing this for a test and it says only the sample surveyed, you would get it wrong. So the confidence interval is so you can, if you had unlimited time and money and you tested 5 billion people on the same product, the survey, you'll get between 3 and 19% would select 8 to 10. So now you got a statistical curve that you can mark it on. And you know right up front that, let's say, okay, 11% is probably who's going to really like the car. But, you know, what are the limits? You might not want to over or under invest. So you could put an investment curve between 3 and 19% are definitely going to love this product. So all across the board, you know the type of return you're going to get. Now you could reapply this by taking different intervals for the lower range, the quartile, lower quartile, upper quartile, mid range. And you might be able to create supplies based on this type of demand. So it's assumed that if 3 to 19% are going to love this car, that you are going to keep a stock reserve within those ranges so you don't run out of supply. And so important to have a confidence interval on what's going to happen into the future. And this is all taken out of finite and linear mathematics and non-linear dynamics integrated together. So years ago, people won Nobel Prizes for the mathematical modeling. So statistics is a big field. Once you get your mathematics under control, your calculus, your differential equations, but then if you are, let's say, an engineering major, you're then going to have to take engineering statistics and probably even today business statistics, finite element statistics, because then you know what's going to happen to those electrons in the wire, how much you're going to turn to heat, how many air molecules are going to slip off the wing, how many cars are really going to go and sell. It's all been proven over and over and over. So that's why statistics isn't just taking records, but it's using mathematical models to predict what's going to happen in the future to, in this case, 99% confidence. Be careful of using words like certain or we assume. Those are bad words in statistics, but you have to keep we are confident. And remember, this is to figure out if all population groups, what they're going to pick. And this is the math behind it. So confidence interval for proportions are very powerful. So last part of this lecture, you might ask a question like, what about the true proportion of those who selected a rank of 1, as in the worst? You know, the people that hate the car, right? 10 is the best, 1 is the worst. So you can re-implement the same mathematical modeling. And of course, I've got to finish this part here. So we have success. Okay, I'll start here. So you got, count these over. Find all the ones. We only want the ones. So if you take a few minutes and count the ones out of 109, 29 out of 109 samples had selected 1. So 29 over 109, that's 0.2661, or about 26.6%. So use the same 99% confidence. You work this out, the success to the failure, multiplied out mathematically, divided into the number of samples, square root, times the z-score, 2.58 for 99% confidence. Rewrite it. You have a confidence interval 0.2661 plus or minus 0.1098. That's a standard error. So you end up getting 16% to 38% are going to hate the car. That's a rank of 1, right? And a rank of 10, well, you can do the same selection. In this case, only one person selected 10, 105. So it would end up an outlier, and you really could just go by 10. So I used 8 to 10 for like. Where is it? 8 to 10 for like, and then you could use 1 for worse, because look how many ones there are. You got like all these people who hate the car, right? So that's how you conduct a confidence interval, and you can use it for anything. I'm just giving a few arbitrated examples. And this was something I actually did take a survey on something people liked and they didn't like, and so it is a very randomly distributed, mathematically acceptable survey. So I decided to use it for this lecture, but this is the formula you're going to want to use to do confidence intervals for proportions. And it's right there. And then you have your z-scores. And if you don't already have this information, but if you're struggling on something, feel free to use this formula, and you'll get the right answers you're looking for. Thanks for watching this video, and have a great day.